So thank you for being here. So the second part of the lecture, for the second lecture. So today we will begin to state the general definitions of the examples that we saw yesterday. And in order to state the main theorem, the main conjecture that we are looking for, first I would like to say a little about covering spaces, right? So yes, I will begin with that. So yesterday we saw what is the fundamental group, right? We say that if we have one curve, and if we have two curves, for example, and we can deform the one into the other, if we have alpha and beta, then we say that we have an homotopy, right? This is what we saw yesterday, and we define the fundamental group of a given space with a base point as all the curves, right? That goes to this space up to isotopy. And this has a structure of a group by concatenation, okay? But the question is, how can we calculate this, no? And why this is important. So we'll see a technique today that is called covering spaces, no? Covering maps. Okay? A covering map is you take a total space and you project it to the base in such a way that this is a surjective map, no? You have to be continuous, such that for each B in the base, there exists an open set containing B, such that P minus B is a disjoint copies. Now P minus UB, when you look at the inverse image of UB, this is exactly a lot of copies, such that each UB, when you restrict P to B alpha, this gives you an homomorphism between B alpha and UB. Okay? This is a covering map. So the classical example of this is when you consider the exponential map. So you can consider T, it goes to 2p it, right? So this will give you something like this, no? You have the circle, you have your base point here, and then you will have something that is turning around like this. And when you look at this point, it will have an infinite number of points, no? How many? As much as the integers, no? Because this is a periodic function, so for each t in the integers, it will have again, and it will be passing, no? So we can think of it as it is rolling, no? As if it is wrapping along the circle. But what is more important from this? Well, this is important, of course, no? But when we can use this technique, in fact, to calculate the fundamental group. And this is why it is really important. So, what do we have? We will consider the group, the deck transformation group. So I will say what is a deck transformation first. So you have E, you have the base, and then you can consider an homomorphism here. From the total space to the total space, but that it preserves the projection, that it preserves the covering map. Okay? When you consider this, then, as we are talking about homomorphism, they will have inverse, right? And then we can consider the set of all of these maps, okay? The phi from E to E, such that this is an homomorphism, and such that P phi is equals to P. And this is a group, right? This group acts on the total space. This group acts in the total space. And for example, in this case, what would be the deck transformation group of this map? Can you see? So for example, in this case, the deck transformation will be the translations, right? Will be the translations. Each time that I take T and I add 1, no? I make a translation, and it will be like just climbing up in the spiral, right? So for this case, the deck transformation of P is equal to set, no? And it turns out that when we have something like this, we have a covering map such that P1, P1 of E is trivial, and E is path connected. Then we will have that the deck transformations of P is equal to the fundamental group of the base. This is one result. But we have a general result. In fact, for what do we have here? So we have the covering space, we have the base, and we have the map, right? Whenever we have, it's just that I have to say a little more. Okay, whenever we have a map between two spaces, with two pointed spaces, then there is an induced map on the fundamental groups, right? Can you see how this is done? Yes? Then we will have an induced map on the fundamental groups. So in this case, For a covering map, then the induced map on the fundamental group of the total space this will be injective, meaning that in fact we can see the fundamental group of the covering space as a subgroup of the fundamental group of the base. And there is what is called a kind of a Galois theory for covering maps that says that for any subgroup that you have of the base, then you can construct a covering map, a covering space and a covering map such that P1 of XH it goes to P1 of P, and the image of this is exactly H. Okay? So we can always construct this. Okay? And what do I want to do this? Okay. And what happened with deck? Okay, I will put it like this. And what happened with deck? Here we will have deck, and deck is always acting on this side, no? What happened with deck? This guy will be exactly the normalizer of H, the quotient with H. Okay? And this is the general scheme that we will have for covering maps. So, as you can see, if we have something like this, no? We can recover the whole lattice of subgroups of the fundamental group by studying covering maps, no? And if we know how to construct these spaces, then we will know how to study the structure of the group, right? So this is why we are studying the algebraic or the trying to construct topological spaces to study the groups. Because if we can construct nice covering spaces, then we will be able to study the whole structure of the group, no? The whole lattice and properties on it, no? And in particular, for this one, no? If we can find one covering space such that it's simple connected, meaning that its fundamental group is trivial and it is path connected, this is called simple connected. And if we have a covering space that is simple connected, then it is called the universal cover. Okay? This will be called the universal cover. Okay? So, okay. a nice example of this. Well, we already have this example, of course, no? But we can construct another nice example, no? That is maybe related with Alfredo's, no? That is, for example, if you take the action of set 2 in the sphere, and you consider this generated by A, meaning A, the map that takes X into its negative, the antipodal, then you can take the space of orbits of this map, as it will be identified in the antipodals. You get the projective space, right? Here you recover the projective space. And in this case, then you will have exactly this structure, no? You will have set 2 acting on S2, that it is projected on RP2. This is a covering map, right? This is simple connected, okay? And then the fundamental group of RP2 is set 2. And then you can have all of this, okay? So, and what else do I need here? Okay. We have talked a little about the fundamental group, that is the first, as you can see, it has a 1 here, no? But we can define what are called the homotopy groups, higher homotopy groups. That meaning that we can consider the same that we have here, functions from, but not just from S1, but for Sn into the space with the market points, etc. And we can give them an algebraic structure, and then we will have Pn, right? So, I will erase here this example. And Eilenberg MacLane space is an space X such that Pn of X is trivial for n greater than 2. All the superior homotopy groups are trivial. Okay? In particular, if X is a CW complex, we haven't said what it is this, but I will tell you afterwards. If X is a CW complex, then this is equivalent to ask that X, the universal cover, be contractible. Okay? And this is what we are pursuing for Coxeter and Artin groups, in certain sense. Okay? So I tell you this little background so we can enter. Okay? Everything is good? Yes? Okay. So, good. Now, let's talk a little more about Coxeter. I can erase this part? Yes? Okay. So, a little recapitulating a little what we saw yesterday, okay? So, we took a S, a finite set. And we define M a Coxeter matrix. And we say that these Coxeter matrices are in bijective correspondences with what we call Coxeter graphs, right? So I can speak about Coxeter matrix or Coxeter graphs, it doesn't matter. And with this, we define the Artin group. That is given by as an abstract group. It has this presentation, no? And we define the Coxeter group as a quotient of this, no? Okay? And we say that we would like to give a geometric counterpart for these objects. So today we will give this geometric counterpart for this object. So, and the main example, no? I will just put the main example. Where this graph with 1, 2, 3, 4, just till n. The Coxeter group was the symmetric group, and the Artin group, it was the braid group. Okay? And yes, let's put it like that. Okay. Just a reminder. We will say a cone on B. It's an space. It's a subspace. It's a subset of B, such that whenever I take lambda of x belongs to E, for any x in I and lambda positive, right? We are taking, this is a cone. Whenever I take, let H be an hyperplane, in B. So what do I need to define an hyperplane in a vectorial space? What would be the main ingredient to define an hyperplane in an orthogonal vector, right? If I take an orthogonal vector, then I can define an hyperplane. So I can put it like that. No? I will put alpha, H de alpha, will be like x in B, such that alpha x equals to 0. This is if it is it's homogeneous, right? But then we can translate it, no? So I will need like two ingredients, alpha and a translation, no? So H alpha T will be H alpha plus the translation. Okay? So in this way I can express any hyperplane, right? And so I can divide the space in two parts, no? The positive part will be exactly the same, but and the negative part and then I can do the corresponding translation. Okay. Okay. So far so good. What I'm just saying is that I have this hyperplane, and if this is alpha, then this will be H alpha positive, and this will be H alpha negative, right? And it is divided in two parts. Okay. How can we define polyhedra? A convex polyhedra in B defined by H alpha by a given family of hyperplanes. So I have different hyperplanes, and I will take the intersections of the semi-spaces defined by the hyperplanes. Okay, is the intersection of subspaces generated by hyperplanes, and it will be convex, no? It is clear, right? Because, so for example here, this will be the intersection of this. This will be a convex polyhedra, right? It doesn't need to be compact, not bounded, right? When we have this, this will be a face, right? This will be the faces of our polyhedra. And the whole hyperplane will be called a wall, okay? So we can distinguish, we will put facets. The facets will be the intersections of the hyperplanes. Facets, the hyperplanes. The faces will be the greater dimension facets. A wall is the support that is an hyperplane, no? Okay? Okay, I think we are good. So let's see an example of this. Let's consider example HK prime XYZ such that y is xz and hk xyz such that x equal to kz. So how this will look? This is a hyperplanes defined by equations. Huh? So when does this look like that? Really? This is in 3 space, no? And this is in 2 spaces. This is dimension 3 and this is dimension 2. So how this is a representation of that? Because we are having the hyperplanes are going like this, no? Tun, 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 tun. And the other ones are going like this. All of them, these are homogeneous. These are passing through the origin. So these two, no? And then when I cut them, no, like this, then I will have, I'm drawing here, no? So in certain sense, what we have here is that in fact, this is looking like this, no? All of these lines are supposed to go to the origin, right? Maybe this should go like this, and this like this. Mm-hmm. Okay. Maybe it's not a good drawing, but it's something like this, no? So these are all the hyperplanes that are cutting, right? Mm-hmm. And in this case, these hyperplanes are cutting the space. Mm-hmm. Okay. I have to say something, yes. Then I will have this arrangement of hyperplanes. We have this and this. Mm-hmm. What it is important is that all of these hyperplanes intersects a cone, okay? And what is the cone here? So we will have the cone will be x, y, z. Like this, okay? Another characteristic that have these hyperplanes, finite, right? Whenever you stand in a point, I will put it like this here. This is is locally finite. It means for any x in the there exists a neighborhood that when you intersect it with the number of hyperplanes in A such that ux inter h is finite. Yes, like this. Okay. So whenever you put in a you stand in a point on the cone, it intersects only a finite number of hyperplanes. Okay. Okay, we have that. And now what we will want to do is to consider a reflection, a set of reflections along these hyperplanes. Okay? We have our ingredients. Now we will consider a reflection. Okay, let's define a reflection. A reflection will be a transformation from B to B such that it leaves invariant H. It is the identity in the, this is the, and furthermore, we ask it to have order 2. This is equivalent to ask that R be a linear transformation, that -1 is an eigenvector, and the fixed space associated to this eigenvector, no? The fixed space of -1 is H. Okay? And this will give you the reflection. The classical reflections will be associated to a bilinear normal form, but in this case we are not, it is not necessarily associated to a bilinear form. When we have a bilinear form associated, it corresponds to the finite case. Well, I will say a little more about that. Okay. So what we have till now? Okay. So here we have, this is an hyperplane arrangement. This is called an hyperplane arrangement. And now let's consider, how can we construct this from a convex polytope? Okay. Okay. This will be called constructing. Let's start with that. Okay. Let C0 be a closed convex polyhedra, no? Okay. And then it has associated a set of walls, right? Let S the walls of C. Okay. And then this will be like, I will put it like A, like this, and I will put S1, Sn be a set of reflections associated to A, no? This meaning that S1 is the reflection along H1, etc., right? And then we can consider W, the subgroup generated by these reflections in the general group. Okay? Then we will call, I will put it like this. This will be the Weinberg This is a Weinberg, no? A Weinberg system. If two things happen. Well, in fact, just one. If the action is proper. Yes, like this. Meaning that when you move the polyhedra, when you move the polytope, it doesn't intersect again. No? It's like tessellating something. If it intersects itself, then it will be a mess. But if the action is proper, if this region is moved to another part, then this will be called system. Okay? So, what is a good example of this? There are many, but I can erase this? Yes? So, for example, when we have something like this, you have something like this. This is one, and this is the other, right? And this is our cone. Well, this will be our polytope, right? This will be our convex polyhedra. And when we do the action, then we will have something like this. It will move like this. And no, it is wrong, huh? This will be moved to this part, yes, and this will be moved to this part, like this. Okay, yes. And we will have something like this. right? And this will be the action of C0. This is C0. And the cone, what will be the cone here? Because all of this is, okay, I didn't put it. Yes. So, and when we look all the translations, WC0, all the translations of this, it will give you a cone. In this case, the cone will be the whole space, no? In this case, it is the whole space. S is the generating set. Is a generating set. Of W. And C0 is the fundamental chamber. Of BWS. Okay? So, the main theorem of B, it says that in fact, no? Theorem 1, let be WS a Weinberg system we define this guy in I as the translations as the union. This is the union. Yes, right. As the union W in W of all the translations of the fundamental chamber. Then the first thing is BWS is a Coxeter group. Meaning that it a presentation as the one that I erased here, right? The second is that this guy, it's a convex cone. With interior not empty, of course. The third thing is that W acts in the interior of I properly and is continuous. That it is essentially that it is inducing a kind of a tessellation of the space. Okay? And the fourth point is that for any x in I, the orbit the stabilizer is non-trivial. It means in particular that there exists. This theorem is telling us, so you begin with a closed convex polyhedra, no? A polytope that is bounded by hyperplanes, Okay? And then you take the walls, you take the hyperplanes associated that are surrounding it, you take the reflections, you consider the group generated by reflections, it's quite natural, right? And then you make it act. If the action is proper on the polyhedra, meaning that in certain sense it is tessellating something, like in this, then it is a Weinberg system. And in that case, then you will have certainly a Coxeter group. So we are recovering no? We are giving we are recovering the interpretation, a geometric interpretation of the abstract group that we gave, no? We are saying that we have these geometrical objects, and from these geometrical objects we can construct that Coxeter groups, no? But in fact, the converse is also true. Meaning that if we have a Coxeter group, on the other hand, no? I will use this notation just to distinguish, because this is a really geometrical object, right? This has associated this set of reflections that are fixed and the polyhedra, etc. No, and with the one that we started before, with just the presentation, it is just combinatorial, right? So the just combinatorial, I will just write it like this. C, the Coxeter, WS. And also notice that the W is different, no? Let's S. Then there exists because here I didn't tell you the presentation of this group, no? And this group is given by its presentation, so in principle they don't have to be the same, no? There exists a such that BW might not be unique. But there is a standard way to construct it that is given through the TITS representation. TITS representation. It's also TITS or canonical representation, no? Canonical representation. This might not be unique. It's canonical representation. Okay. Okay. So now we have these two words. Maybe yes, I can do another example. Yes. Well, just to again the symmetric group. No, I will do two examples. Again the symmetric group. If we consider C0 X in B such that X2 like this, xn minus 1. And then we have hi j defined by xi equals to xj. That is all the diagonals, right? Then C0 is the convex polyhedra that is bounded by it, right? Bounded by this. Okay? And so the walls H1, 2, H2, 3, H3, 4, H4, Hn plus 1, I suppose. So here you can see already that these are the transpositions that we are looking for, right? And then the symmetric group Sn, well, W in this sense W is the group generated by S12, S23, S34, etc. Sn n plus 1. And in this case, I will be again the whole space. All the set of reflections, when we look, all the set of reflections are the reflections Sij, no? And this is called the braid arrangement. Okay? Okay, this is one example. Another example I will put here. So this will be in R2. So we will define decay, defined by x equals to k, decay prime defined by y equals to k. Okay? So this, how this will look? It will look like this now. And so let A consider with this decay and decay prime, and we have all of this. So here we have a lot of a lot of hyperplanes, no, a lot of planes, but we need to choose. So let's choose, for example, one chamber. We will choose like this. And then we will need to see what is the presentation of this. Okay. Then we will have W of this. Let's take this S0, S1, and this to be S0 prime, S1 prime, right? So this will be generated by S0, S1, S0 prime, S1 prime. And this is generated inside of GLE2, right? What will be the presentation of this? What are the relations? S0 and S, for example, this and this have a right angle, so they will have like S0, S1 equals to S1 prime S0. No. S0, S0 prime equals to S0 prime S0. This commutes. And the same goes in this case, no? S1 commutes, S1, S1 prime commutes, S1 like this, S1, S1, S0 equals to S1, S0. And when I write it as a Coxeter group, then it will look something like this, no? I have 4 generators that are the walls that that surrounds the fundamental chamber. And the relations will be here I need an infinity, is 1, is 0, is 1, is 0, prime, prime. And this is the Coxeter graph. Okay? As you can see, all the relations are given among the relations on the walls of the chamber. Okay. So for this, there will be an exercise in this for this example, and the exercise will be to find all the different kind of elements that we have in this. No, of course we have already the reflections. We will have, if we compose this one with this one, we will have a translation. But what kind of other transformation can we have here, no? So homework here, exercise. Find the different elements of W. Okay? Okay. I will continue here. Okay. I erased this. Okay. So we have our group. We have our Coxeter, now we know that if we have a Wimber system, we can have a Coxeter system, right? And backwards, no? So we can pass from one to the other. But in this sense, in this way, when we consider a Wimber system, then we will have that this will have associated a chamber, no? A how did I call it? Fundamental domain. And we know it's this cone, no? That it's the union of all the orbits of this. Okay. Then we have this. What are the ingredients? We have our we have the cone, we have our hyperplane arrangement, flexion. Okay. Then we will define this space. Once that we have a Wimber system, we will define, if we have a Wimber system, we have an hyperplane arrangement, and from a hyperplane arrangement, then we can define what follows. We will have the cross product of the cone, and we will take out copies of the hyperplanes. Okay? There is a note. That when the group is finite, then I it's equal to B. And this is a result of Coxeter. Okay. Okay. And so we have that W, that the Coxeter group acts on the cone, right? In the interior of the cone properly and discontinuous. And furthermore, we know that it acts moving the fundamental chambers, right? So we can consider the action of W in this space. And then consider the space of orbits. And this, we'll call it like this. Okay. Van der Leck. In the 80s, what I think is that we have this. So with all of this, the theorem of Van der Leck is that the fundamental group of NA the Artin group. Well, I will write it better. So, Wimber system, right? And from the Wimber system, we already know that we have a Coxeter system. And from a Coxeter system, we can associate a graph. No? It has associated a Coxeter graph. And also from the Wimber system, we have all of this. No? We have our cone, we have hyperplane arrangement, and the reflections. Okay? The theorem of van der Leck says that when you consider the fundamental of NA with the Artin group of the Coxeter system that we have, no? And furthermore, we have here, no? We have that our group is acting properly and discontinuously on this covering space, no? On MA, and this have a quotient MA over W, that it is NA, no? So it will have associated a short exact sequence, no? Meaning that we already know that this, when we pass to fundamental group, this is the group of gamma. This will be the Coxeter group of gamma. And the kernel is what is called the colored Artin group. And then this will be the colored Artin group. Okay? This is the theorem of van der Leck. And as you can see, we need like a lot of ingredients to construct all of this theory, no? Because it is quite geometrical. But now that we have all of this, is the main conjecture, the KP conjecture is the following. I will put it here. So this is not the universal cover, right? This is not a universal cover, and in fact, this is a really topological space that that it is defined here. To do the calculations of this group by means of geometry, it takes a while. It is possible, but it takes a while. So the KP conjecture is that when you consider the universal cover, this is contractible. If this is contractible, by what we saw at the beginning of the lecture today, then this will mean that this group is a KP1, right? That this space is a KP1. It's an element MacLane space, right? Because it's a universal cover, it's a KP, it's contractible. So this is what is called the KP1 conjecture. And this is, in certain sense, what we are trying to solve. So, we can have two flavors. As you can see in this theory, we can have two flavors. We can have a completely combinatorial flavor and a geometric one. So, the aim of the rest of the talks will be to unify them, to give a bridge to see how this works in both worlds. So, I will tell you in the last 5 minutes that I have what has been done and what is the main strategy to do this. Okay? So, as you can see, this space is quite complicated. This space is quite complicated because then you have to look to the plane and then to not only to the vectoral space, but the 2 times the vectoral space, and then consider the hyperplane arrangements, etc. No? So, what people did in the 80s and in the 90s is the following. They construct something that is called Salvetti complex. So, Salvetti complex first was defined by Salvetti, of course. Taking an hyperplane arrangement. So you take an hyperplane arrangement, then you can make like put an order on the hyperplanes and etc. And from this, you can, this is a geometrical construction. But on the other hand, you can make a construction of the Salvetti complex by means only on the graph, by taking certain subgroups. No? This is a combinatorial construction. And why it is important, the Salvetti complex? Because the Salvetti complex has the same homotopy class, has the same homotopy type that NA. Well, first we have to see this. We will see the construction in the geometric sense. We will see the construction in the combinatorial way, and we will see that in fact the Salvetti complex has the same homotopy type as the space that we are looking to study. Once that we see that it has the same homotopy type, then what we want to see, to study, is its cellular decomposition. If we study its cellular decomposition, then we can deduce, no? Or we can reprove the theorem of van der Leck. Meaning, we can see that we have all of this, and we can recover the presentation of the, well, we can see that in fact it coincides with the Artin group and the Coxeter group, etc. Okay? So we recover the theorem of van der Leck, and once that we have all of this, we will see 2 other things. First, we will prove the KP1 conjecture. So let me tell you a little more. The KP1 conjecture was was solved by Briescon and Saito in the 72, and also by Deline again in the 72 for when the group is finite. When the Coxeter group is finite, it has a proper name. We say that are of a spherical type. And then by Charlie Davis for FC. And another, no? Paris for in the 2012 generalizations. Okay, so what we will do is to recover this. We will recover this demonstration. We will recover. But in modern, we will recover the demonstration. No? We will recover. We will have KP1 for a spheric. We will prove this, and if we have enough time, we will see we will see a generalization of this complex that will allow us to solve for many other kind of groups of this type. Okay? And that will be the plan for the rest of the talks. Thank you.